All right. So, welcome everyone to the C Programming Language Workshop. This workshop is going to really serve as more of a general introduction to the C programming language. It does kind of expect background on other languages. Yes, you can basically, if this was your first time learning anything about programming, this would be a decent place to start. But I'm going to try and keep it a bit more high level since I know basically everyone here is at least familiar with programming, right? So we're basically just going to be going over all of the core language features as a reminder to everyone, and hopefully there'll be some other cool stuff in there, even if you know the C language already, that you may not have known about, some little side stuff. So to get this out of the way first, here's a brief overview of what we're going to be going over in this workshop, right? So the first thing I'm going to go over is just a bit of the history of the C language, the importance of the C language, the features of the C language, and then we're going to go into basically how the C programming language works. We're going to go over how to declare variables, operators, control structures, pointers, arrays, strings, and structures. So it's basically like ICSI 201, but for the C programming language in 1.5 hours instead of an entire semester for Java. And then finally, I thought I'd talk a bit about installing a C compiler on your machine, which can be extraordinarily tedious if you don't know how to go about it. And that's really one of the main reasons why you don't see more people programming in C. At least that's what I like to chalk it up to, because installing a good C compiler, especially if you're on like Windows or Mac, can be a rather tedious process. You don't always have to like build from source, but sometimes it's getting pretty close to having to build from source, and it gets quite annoying, especially if it's a special custom opera or compiler distro. We're probably going to be using GCC, but there's also CLang and everything else for those of you who know about CLang. Anyway, and then finally, I thought we would end with writing some simple algorithms and going over some common pitfalls together for the demo section, which you can write the algorithms independently or you can follow along. And we will go over all of that. And before I get any comments, yes, most of the slides are cut-paste from Tutorials Point. I'm going to be providing my own commentary over a lot of what they have there. But just to give everyone, personally, I didn't think that I was qualified to give a really good introduction myself to write out all of the slides. And I think, personally at least, I think Tutorials Point does one of the best tutorials for the C programming language, like, of all time. Like, when people ask me, where should I learn C? I always point them in the direction of Tutorials Point, because I think that their entire section on C is very on point. I don't know about other languages, but they seem pretty reliable overall. So in that case, now that you guys know the general structure of what we're going to be going over, let's actually get into it. So the first thing we want to go over is the history and the importance of the C programming language. So I'm sure all of you know that C is one of the most important programming languages of all time. It was really influenced by like the first languages. Like when you think of like the first languages in existence, we're talking like ALGOL, BCPL, and BCPL actually influenced B, which there's a joke that the actual order that's supposed to happen is that they named it C not because it was after B, but because C was the second letter of BCPL, which means the sequel to C should actually be called the P programming language rather than the D programming language, which, for all of you who know, the D programming language is an actual thing that they tried to follow up with C. Anyway, so this is C programming language. It was originally developed by Dennis Ritchie at Bell Laboratories, and that was in 1972. So really early on, actually. Not super early, like not the 60s, but in the 70s, early 70s, right? And the real big innovation of C was like the fact that it was a strongly typed language, right? Like you had strongly typed languages before this, but this was the first one that had like really nice control flow on top of being a strongly typed language. And it interfaced really nice with the low level stuff. And we'll go over that next. So it was really developed right alongside the Unix operating system, which of course, eventually was the foundation for later operating systems like what we use now, like Linux. And I believe Mac OS or OS X is actually directly descended from Unix still. So basically, it was strongly integrated, of course, with the Unix system. And essentially, C was finally standardized into what we call ANSI C in 1983, which was quite a big development. And this is still one of the official standards that you see a lot of, especially older operating systems. They'll be written compliant to ANSI C. And then finally, we got the ISO, the International Standards Organization, to actually get C officially standardized in the ISO format. And then we had C89, and all subsequent C standards are standardized by the ISO. So then you'll see like C99, C11. C releases much more slowly than other languages like C++, which is like every 3 years. C is kind of like every 10 to 12 years in its release cycle. All right, so let's take a look at the history of C, right? So this is, as previously stated, we started out with Algol, then we went to BCPL, and we got B, and then finally Dennis Ritchie, traditional C, and then the famous book, Kernighan and Ritchie. If you've ever seen I almost feel like I should pull it up, K and R C. I hope you've seen this book. This is like a very famous picture, the C programming language, right? This is by far one of the most influential books in computer science. I think there's probably better tutorials out there now, but this was really the book that started it all. This was like for about 30 years, this is what C programmers, this was like the C Bible, basically, that everyone had a copy of. And of course, it was written by the guy who developed the language, right? So, Richard. So, you can't get much better than that. Anyway, so let's go back into the presentation. So we had traditional C, then we had the book, the famous book, and basically the book set the standard until finally, years later in 1983, we had ANSI standardized C to get ANSI C. And then finally ANSI ISO C, and then then we get C99, which C99 is now widely considered like the most popular version of C. If you're programming in C, you're probably using C99. Sometimes you have to specify that you want a later version for some new spicy features, like C11 features. They add some new stuff in the libraries, but really C doesn't evolve that much. It always stays really close to its core roots of traditional C and K and RC. Like, they're never going to add a try-catch block to C. It's just not going to happen. They're never going to change structure. They might change the libraries a bit. And really, all of the new implementations of C are only changing the libraries. They're not really touching the structure at all. So that's just a brief overview of the C programming language and the history of it. So now let's talk about why it's actually really important, and like why C is like, it was such a bombshell when it was released, and still to this day, you hear people like Linus Torvalds, when he developed Linux, he explicitly said, no, we're not going to use C++, even though it offers a richer feature set. We're only going to use C. Like, people love the C programming language because of all of its features, despite its simplicity. And that's really what makes it one of the most popular languages, is the fact that it's simple and effective at what it does. So what it actually offers is, first of all, a rich set of built-in functions. Now, what I assume they're talking about here is its library functions. C provides a great starter library that's not too big, but also provides a lot of functionality. So we're talking like the string library. Like, it's very simple stuff, the math library, all of the implementations of that, it can be implemented very easily, but it's a rich set of features that's included with that standard. So basically, also, we can use operators, which this is, I assume they're talking about this being an increase in, ability from assembly language, in which you weren't actually using operators. You were using statements to, add numbers. And you even see that transfer over a bit into stuff like BASIC and Lisp, where it was like, I think some of the earlier implementations of Lisp, you actually had to type out add and then the numbers to add numbers. C was like, no, we're not doing that. We're going to use the operators. So C, of course, has a very rich operator system that we are going to get very deep into later on in this presentation. If you thought PEMDAS was bad, just wait till you see C operator precedence. Okay, so let's continue. So yeah, C combines the capabilities of assembly language with features of a high-level language, and I'm very excited to talk about this tomorrow, because you really can see when you get down into the nitty-gritty details of C that C was designed to work beautifully with assembly language and really have like a one-on-one correspondence where you can call C functions from raw assembly code and you can call assembly from C. And there's even languages go so far that you can literally call inline assembly as well. And a lot of compilers offer support for that. And that's why you see C so popular as like a high-level language that you can use at the low level, especially for operating system programming, which is what this workshop series is really all about. You'll see that the C language is the obvious choice for an operating system high-level implementation because it just translates so well down to the assembly that you're going to need in your operating system. There's no way to get around a lot of the assembly instructions, and you have to do some stuff in assembly, but you want to do most of it on the high level still, which is why you're going to be using C for all of the high level stuff. And you don't want to have to write out individual assembly instructions. So, continuing, yes, it is. I think this is supposed to be suited. It's well suited for writing system software and business packages, which, yes, C is also great for writing system software. Business packages, modern day, probably not. You'd probably want to use something that's a bit easier to develop for with a faster development cycle like Python or something. But overall, the C language has... Oh, welcome back, Tony. You're echoing. My bad. So essentially, yeah, modern day C isn't really used that much for business packages, but especially on embedded applications like industrial equipment and whatnot, C is still the language of choice. So if you consider that a business application, then potentially, but that's more system software, I would say. Anyway, so continuing, C is insanely fast. I'd like to pull up my C benchmarks here to show off how much I love C. Whenever someone brings up how great Python is, I always pull up the C benchmarks. Let's pull them up. I want these ones. Yes. This is okay. As you can see, this is Sudoku solving and matrix multiplication with different compilers and languages. As you can see, C performs exceedingly well compared to other languages that are popular. Python, in particular, is not supposed to be fast. It completely falls apart when it comes to getting things done fast. However, Python is able to be developed much faster. And also, not to mention the fact that Python, the reference implementation of Python is CPython, which is written in C because they want it to be as fast as possible. And also, every single major Python library that needs to be fast, the backend, it's all written in C. And it's all just calling into C code, like TensorFlow, all the machine learning stuff that you do with Python. Everyone's like, oh yeah, Python is so great for machine learning. And it's true. Python is a great interface into machine learning. However, behind the scenes, NumPy, TensorFlow, PyTorch, it's all written in C. And you're just calling C functions from Python. So, and you can see everything else here as well. Even other compiled languages, like, where's Java at? I like making fun of Java. Can I find Java? Java is still slower than C, but as you can see, since it's also compiled, it's still relatively fast, right? JavaScript is just-in-time compiled, and you see just-in-time compilation, kind of middle of the road performance, but it's nothing like C. C is exceedingly fast because C gets translated. C is so heavily optimized when it comes down to assembly instructions that you are getting every single piece of optimization you possibly can. And even if you hand wrote the assembly, the optimizer for a C compiler would probably beat what you could write for your algorithm. That's how smart the compiler is when it comes to optimizing the assembly code, which is really what's running and making it so fast. And all right, let's go back to the presentation. So the final thing is the fact that C is highly portable, right? So if you have C code, so this is interesting. It's highly portable as long as you account for the fact that different operating systems operate differently. But yes, C is much more portable than assembly language, and C was one of the first languages where that was really made clear because you were able to write applications in C and basically just hard code in different options for different operating systems. And you can still see that in a lot of modern libraries. You'll see it like, oh, check if it's Linux, check if it's Windows, check if it's Mac, and then do things based on that. So that's not modern day, that's not considered very portable. But back in the day, this was a major innovation because you could run this at least parts of the same code on different processor architectures, right? All right, and then finally, C has the ability to extend itself through structure declarations, which is very exciting, and that's really what made C one of the best languages. And this became so popular eventually, like the idea of structures was really what led to object-oriented programming later on. Like C structures influenced the languages that then influenced C++ to come out of C, essentially. So basically, you have the ability to extend the data types yourselves and finally get to very high level complexity and abilities through this self-extension. So also, finally, C is a structured programming language, which means you have the ability to think algorithmically when it comes to C. And you'll see this a lot when we look at the actual C algorithms. But it's actually, when you're programming in C, this is one of the most important things because, and you see this carry into every other language, right? Like almost every time, like when we think about pseudocode, normally we're thinking in C pseudocode. C was really the language that started this style of structured programming and just mentally going through the algorithm structures as if they're blocks and modules. So we'll be able to see a lot of that later on. For those of you who have familiarity with Java, it's essentially the exact same thing as Java. Java really based most of its functionality, at least the non-object oriented part, on C control structures. And that'll become exceedingly obvious going over the actual C programming language, which we're about to get into right now. So this is Hello World. I thought this was a fun place to start. Hello World is always the first thing you learn in every single language. So I thought we would briefly go over the different parts of Hello World. For those of you who may not be familiar with the C programming language, obviously it's a bit more intimidating than JavaScript, which is just console.log hello world, or Python, which is just print hello world. This you actually have to have some boilerplate code to get this set up. So of course the first thing you have to do is output is not included by default. So you actually have to include stdio.h into your program to tell it that you want to be able to use printf. So that's what this first thing up here does, is hashtag include. Any statement in C that starts with hashtag is a preprocessor directive. And the preprocessor is a lot of fun. It runs before the compiler and performs text replacement. And you're probably asking yourself, well, what do you mean text replacement? I just want the function in the library. But what's actually going on here when you do hashtag include, it is literally copying every single thing from this file and inserting it as text right here above the main function. So you're actually importing a lot of stuff you don't actually need. There's ways to get around this using pre-compiled binaries and then having the linker take care of it, but I'm not going to go into that. And for all intents and purposes, we are going to pretend that this fully includes all of the code for printf just right above main. You should always remember that include is literally just text replacement, and almost every preprocessor directive is meant for text replacement options rather than actually, it's not doing some magical import magic like JavaScript or any other language like that does. Java, I don't even know how, does Java, I'm not even going to go into how the Java package system works because you have to use their special import statements and everything. I'm pretty sure the compiler is linking with this. Anyway, this is literally copying the text in this file above main. So anyway, then you're going to see this block right here, int main, and you can see it has a closing brace right here, and then everything indented. This is the proper way to indent. You indent two things in for your block. Anyway, so this is a function, and we will get into functions quite a bit later. But for all you need to know now is the fact that essentially anything inside of these braces inside main is going to run when you start your program. And the first thing that happens when you start your program is any code inside this main block runs, right? So essentially all we're doing here is saying All right, print out hello world at this thing in text, in quotations. That's a string. I hope all of you know what a string is. The fact that you're here probably means you know what a string is. So I don't think I have to go over that. But essentially, printf just displays something to the terminal. And in this case, it's hello world, and that displays. And then you're going to see we have a return 0 here. This is actually optional for the main function, but every other function that's not a void function has to have a return 0. And you can see int here. This means we're returning a number from the main function. And as you can see, we are returning a number. We're returning 0. And there's a lot of opinions on what you should return, but in general, a C program, and any program for that matter, you should be returning 0 if the program executed successfully. I know it seems kind of counterintuitive because 0 is false in if you think about it, but in this case, you always want to return 0 to mean success, and otherwise, this is kind of a carryover from older programming languages where you would return an error code if something went wrong, and 0 was the code that meant nothing went wrong. Anyway, we're going to continue here. This is another little snippet that just basically shows the general structure of the main C program. You start off with your function name, which is main in this case. Then you have your opening brace to start the main block, and then you put statements in here, and then you end the program. And statements are basically lines separated by semicolons, which I'm sure you're all familiar with. And what's actually funny about the C programming language is you can declare main in quite a few legal ways, and I actually didn't even know it was legal, but apparently you can declare main without a return type and literally just say main. And you can do that with any function, and it implies an integer return type, which actually blew my mind this morning when I found this out earlier today, because I've been programming in C for 5 years. This is 100% cursed knowledge. Never do this. Never start your program like this. Always put an int or a void. All of these statements are essentially equivalent. Actually, some compilers don't like void main, and they will not let you do void main. I've seen it before. But you can also put a void in the parentheses to let it know that it's not taking anything. Sometimes you do want it to take parameters like argc and argv, but we're not going to discuss that. That's a bit beyond the scope of what we're doing here, since we're trying to get everyone ready for operating system development, and that's more for command line software development. Anyway, let's actually get down to, now we're going to talk about variable declarations. So the first thing you need to know is that C is a typed language, which means every piece of everything that you declare in the program needs to have a type. And the type, while it looks nice for us to know what the type is, it also serves an important purpose behind the scenes. The type lets the computer know how big whatever it is behind the scenes. So a character is typically a single byte. And everything, and I literally mean everything in the C programming language, every single thing is literally a number. Everything is a number. Char, this is actually a number. It's 0 to 255. Int, this is a 32-bit integer. Floats, even though they're treated as decimal points, behind the scenes, they're also everything is in binary. And that's what's so great about the C programming language, is the fact that every single type, you can view it as basically just raw binary if you want to, and operate on the raw binary yourself. And that's in heavy contrast to a language like JavaScript, where they quite literally abstract things out of your control, and you will never have access to the raw memory and pointers behind any of your JavaScript objects. Same with Java. Well, Java is a bit more of a special case because everything is a reference. In C, everything is a number. And you always will have access to that number, whether that be even your functions. You can get function pointers to them, which are just numbers that represent memory locations where your functions are. And you just have raw access to that. No other language besides derivatives of C, like C++, offer that kind of powerful functionality that we're going to get into later. So yes, you can declare characters, integers, floats, doubles. Floats are floating points, numbers with decimal places. Doubles are also numbers with decimal places. If you've taken Java, these look familiar. All of these types look familiar, I assume. Does Java have a char? I'm pretty sure Java has char as base thing. I think Java also offers byte. Do they offer char? I know they offer string as a default thing, but as for character, I'm not entirely sure. There might be I'm sure there's probably a wrapper for it. Anyway, moving on. Let's take a look at some more advanced integer types. So this is fun because not everyone knows about the fact, and especially most programmers never have to deal with the advanced integer types, right? Normally, if you want a number, you just say, "Oh, I want an int." If you want a character, you say, "Oh, I want a char." If you want a decimal, number, you use float, or normally you just use double. You don't even care about float. You're basically just told, "Oh, only use double precision." But operating system development is different. We actually really care a lot about the length of all of our numbers, because a lot of functions and whatnot only take operators of a not operators, but memory of a certain length, and you always want to make sure that you're storing the right value. So a character is 1 byte, right? An unsigned character is also 1 byte. So these are the signed and unsigned modifiers, essentially. So you can add these modifiers on to tell it if you want to use negative numbers or exclusively positive numbers. And really, it's only telling it how it should be interpreted. Internally, it's still the same representation, but it's you can basically change how it's interpreted. So here we see that an unsigned char is 0 to 255, but a signed char, on the other hand, you get the negative range, but you're basically cutting the max value in half to be able to access these negative numbers, because we're representing the lower half with the upper half of that range from 0 to 255. So then we have int, which is 2 or 4 bytes. It's almost always 4 bytes on modern systems. These are the minimum requirements, but in reality, ints are always 4 bytes, or 32 bits for that matter. And we can see in that case, we can store up to 4.2 billion, and that's actually the reason why 32-bit computer systems have a RAM limit of 4 gigs of memory, because you can only access up to a 32-bit address, which the maximum in this case is 4.2 billion. Next up, we have unsigned int, which that's what we just did. It's you're going from 0 to 4.2 billion. Here we're going to half of that, right? Which is 2.1 billion. But we have access to the entire lower half of that scope as well. Next up, we have shorts, which is 16 bits or 2 bytes. And this can store up to 32,000. This is probably the rarest data type. You almost never see anyone using a short. There's almost no reason you would want, unless you're using a operating system dependent structure that requires something that's 16 bytes or 16 bits. You're almost always going to opt for a 32 bits. And no one, at this point, there's really no point to using shorts, because nothing runs in 16-bit anymore. It's all 32-bit processors, 64-bit processors. So the entire purpose of the short has kind of gone by the wayside. And short is probably going to be the rarest thing you see. Almost always, though, when you need a number in C, you're just going to be using int, right? And that goes for every other language as well. Like, everything has inherited this, right? Like, Java has inherited this. I'm pretty sure I don't know about C#. I think they've inherited the int. C++ has inherited the int as well. Of course, you see lots of languages nowadays, like Python and JavaScript, where they're not typed, but they still use numbers, essentially. And some of them even have int as a reserved word. I believe JavaScript has int as a reserved word. And Python uses int as the cast to cast any other data type to a number, if you want to interpret it as a number. Anyway, moving on here, we have unsigned short, which, as you know, just increases the range you can go to. Long, which is 64 bits, essentially. But for a 32-bit operating system, long will only be 32 bits, because, of course, you can't store that. And long is normally what we're... So even, this is actually really interesting, because even on 64-bit systems, even though we have access to 64-bit integers, we're typically not using them. We're still using 32-bit integers regardless. And then finally, unsigned long. This is basically the longest thing you can get on modern processors. This is the 64-bit integer limit that you can go up to. Anyway, this is fun. I'll go into more of this later in the operating system development night. I'll show you that I basically define all of my types to have different byte widths for different purposes, and we'll actually get to see some of the reasons you would want some of those alternative uses. So let's go over variable definitions real quick. So to actually define a variable, right, you put the type and then you put the name of the variable, or you can do a variable list if you want. So type is a C data type, right? And the variable list, of course, they're calling it variable list here, but normally we're just used to seeing a single variable. And we're also used to doing the assignment on the same line. So this is probably more in line with what we're normally doing in C when we declare a variable. So we can say, for example, let's go down here. Int d equals 3. This is creating a variable named d of size 32 bits and assigning it the value of 3. And as you can see through here, I don't know why the heck they have byte. Is byte? I don't think byte is a valid C. Am I crazy? Let's check this. Byte C equals 3 is not real. I don't know why the heck they said byte. That's clearly not a real thing. Not a valid type. Anyway, you can also see that you can do things like char x equals the single quotation marks. Now in C, single quotation marks are not like double quotation marks. Single quotation marks quite literally translate whatever it is as a integer, essentially, into its ASCII value. You almost could consider these as being like the ASCII convert operator, where whatever ASCII character is in here gets converted into its ASCII value. So x is going to get converted into the ASCII value of x and get stored in this character. Anyway, next we have, so does everyone, I assume everyone understands the basics of declaring variables in the programming language, right? Like this is very similar to every other language you could possibly want. Like in I equals 3, we could do int b equals 1000. You can also declare things in fun ways like, and of course you can do assignments to other variables. Int b equals I, right? Where now we're taking the value we got from, just ignore the assembly output, by the way. we don't need that today. We're going to need that tomorrow. As you can see here, though, we can do fun stuff like b equals I. So now b is going to be equal to 3, and then we could just return b as well if we wanted. And of course, these are, it's the name of the variable is just an identifier, right? So we're just referring to it like that. Anyway, let's move on. I have a feeling you guys are probably bored to tears by the fact that we're going over how to define variables in C, right? So this is where things get a lot of fun. I love my operators. There's so many good operators in C, right? So first, let's go over the standard arithmetic operators. These have been taken by almost every other language. You're going to see these in basically every programming language that's a derivative of C. Even languages like Python, which hate C, claim to hate C, have basically still taken quite a few of the arithmetic operators like modular division, normal division, all of the normal things. And this has basically gone into every other programming language since C. And it was, I don't believe C was the thing to invent this, but it certainly did propagate it out into many of the other languages we see today, right? So for these examples here, we assume A holds 10 and B holds 20. This should be relatively straightforward. If you do A plus B, you get 30. If you do A minus B, you get negative 10. A times B is 200. B divided by A is 2. This makes sense to everyone, I assume. Now, modular division is the remainder after division by a number, and you primarily use this, at least I primarily use this, when I'm working with a multi-dimensional array, which I'm probably not going to go into tonight, but keep in mind that this is actually, people, especially when they start programming, they think that they're never going to have a practical use for the modulus operator. And there are a lot of operators that I'm going to go over tonight that you've probably never heard of and you will probably never use again, but that they do come up. But the modulus operator is actually very common, and you're going to have a lot of problems where you can use the modulus operator to solve something very efficiently. That normally you'd really be thinking through, and it's very common in interview questions as well. So keep your eyes peeled for the modulus operator. Even in other programming languages, you should know that modulo is a very important operation that you can use to your advantage when programming. Anyway, next up we have the increment operator. Oh, Matthew has used the modulus operator when using a hash function and needing the answer to fit the size of it. Yes, this has been, you can use the modulus operator to basically create like hacks into, you can create a very simple hash function with the modulus operator as well, which is very interesting. And I'd love to see a presentation on that at some point, Matt. Cybersecurity implications of the modulus operator. Anyway, next up we see the increment and de-increment operators, which this is actually why the programming language is called C++. It's a joke that C++ is the name of a variable called C plus 1. So essentially it's the next version of it. So as you can see, A++, if A is 10, then the result of this expression A++ is 11. And we also have A minus minus here is 9. And yes, you can quite literally write that, and I'll show this off because this is actually cool. You can see that these compile all to the same thing if we use these operators. So let's get in A equals 10 as we saw as they have. And then let's do three things that are actually all the same operation. You do int A, or we'll say, I want to evaluate the expression, so let's just say int C equals, no, you know what? We'll keep it as A. We'll do A equals A plus 1, A plus equals 1, and A plus plus are all the same operation. And let's see if we can actually see what's going on here. Okay, ignore this last line. This doesn't actually, the compiler explorer is actually wrong. But as you can see, the actual assembly instructions for these 3 lines are all equivalent. They're all doing 1 plus the operator. Essentially, this represents A, this memory location. Right here, this is A. So it's essentially saying, this top one, it's saying add 1 to A. The middle one, add 1 to A. The bottom one, add 1 to A. And these operators, despite the fact that there's 3 of them, and this one especially is long and convoluted, it's all the exact same thing. And languages like Python actually don't like that, and they've removed these from the language, which actually trips me up quite a bit. I really like my increment and de-increment operators in C and C++. So whenever I go over to Python, I always try using them, and much to my dismay, they do not exist. Anyway, next we have some fun relational operators. So a relational operator, and people get tripped up on the relational operators quite a bit. Relational operators take 2 numbers, 1 on each side, and they return true or false. And by true or false, I mean 1 or 0. Because there's no such thing as true or false in the C programming language. In fact, there's no such thing as true or false in any programming, at least, actually that's not true, because Python has like actual types for true and false. In C, true and false is quite literally 1 and 0, and you actually have to include bool. So if we actually want to see the results of, let's actually have some fun here. We can see, let's say A equals 1, or let's say A equals 10, and we'll say B equals 20. Okay? So we can actually see in the return value, if I can get the, I don't think I X'd out of the thing, did I? Nope. Okay, that's the same thing. That's unfortunate, because I would very much like to compile to binary and run the compiled output. Let's see if I can actually get the output once this compiles. So if I do A equals B, we're going to see that this actually returns 0, not, oh boy, that's fun. Can I take a look at the output? Okay, so let's talk about what's going on here, right? So we're assigning 10 to A, we're assigning 10 to B, or 20 to B, my bad. And then we're comparing, does A equal B? We're returning that, right? So this is what the program returned. And we're returning, does A equal B? And we're getting 0 out, which is, no, it doesn't. But if we change B to 10, we are going to see, voila, it returns 1. And these operations, they quite literally return 1 or 0. That is not typed. And this is just to continually enforce the idea and get this through everyone's heads that the C programming language, everything is a number. There is no magical bool or type wrappers. It's all everything raw numbers that you have access to, right? So we can also say if this is B is 20, we return that. We're going to go check if A is greater than B. Clearly, A is not greater than B. We're returning 0. Is B greater than A? Or is A less than B? Yes, it is. Return 1. And we can go through this for every single operator here. But I'm sure you guys get the general idea, right? We're taking in a number on one side, a number on the other side, and that expression is evaluating to 1 or 0, representing true or false. So we have essentially is equal to, is not equal to, greater than, less than, greater than or equal to, and less than or equal to. And these are going to be, I'm sure everyone's probably pretty familiar with these. They're very common operators that you're going to use, especially for conditionals and program control flow and everything. You're going to be using these a lot. All right, so next up, we have the logical operators. So the logical operators basically check whether two statements, they take in a true or false on one side, true and false on another side, and return based on the truth value of, I'm sure, does everyone know logical and logical or? Like, do I have to explain truth tables to people? And is true if both A and B are true. So if A is true and B is true, then this statement is true. If either of these is false, or both of them are false, then this entire statement evaluates to false. Or on the other hand, if A is true or B is true, then the entire statement is true. Or if they're both true, the entire statement is true. But if neither of them are true, then the statement is false, right? This is normal logical usage of these. Does anyone have any questions about this? I feel like I'm not really sure what level I should be presenting it. This is the redstone section. Yes. We can go on Minecraft and build a computer after this, which if you haven't done yet, that's a great idea. I highly recommend doing that if you're in electrical and computer engineering. So basically, yes, 1 means true and 0 means false in the C language, Carter. Good question. That is, yes, everything in the C programming language is quite literally a number. And what's really funny is the fact that C provides a header, include, it's called bool.h, and it gives you the words true and false. What don't they like? They don't like bool.h? Is it not called bool.h? Am I insane? I might be insane. Oh, it's std bool. That's it. Hang on, let me get it back. stdbool.h. There we go. All right, so what stdbool.h does is they actually give you the words true and false, except what this really is if you return true, you're going to see it returns 1. But what's actually going on here, if we actually look inside of stdbool.h, all we're going to see is the fact that they've actually just defined, they did define true as 1 and define false as 0. And they just throw that in there. And the reason they're doing these defines instead of just being characters is because they want you to have more general ability to place these in whatever the heck you want. It's going to interpret the raw things as whatever the compiler can throw it into, or it will use the smallest. We'll get it more into that in the compiler section, but for now, this is essentially how C treats booleans, is that true is just 1 and false is 0. And that's literally basically the exact lines word for word in the std bool header. Okay, so continuing. Finally, the not operator is a single, it takes a single parameter instead of a double parameter. So for example here, if we run not true, we are going to quite literally see that it just flips over to 0. But what this is really saying is you're either 1 or you're 0. So I can literally run not 0 and get 1 because 0 is false. Or I can run not 1 and get 0. because it just flips it. And if I run something like not 12, it's going to interpret anything that's not 0 as 1. And this is an interesting analysis. This is an interesting point to note as well, that basically it treats anything that's not 0 as true. Even if it's not 1, essentially we want to think that it's always in this nice binary, that true is 1 and false is 0. This isn't true. Anything that's not 0 is considered true to the thing. So for example, if I have an if statement and I say like if 12, it actually is going to think that this is true. And it's going to jump into this no matter what, which is hilarious because this doesn't mean anything, but this gets evaluated as a logical Boolean expression, right? It's not 0. This only fails if you're passing in a 0 here. If the whatever expression is in these parentheses evaluates to 0, and 12 does not evaluate to 0, so it ends up just thinking that this is legal. Like, but of course you would never see this in production code, because why would you say if 12? It doesn't mean anything. You actually have to, this makes more sense if you're returning 12 as an error code and you're saying not, if you're doing like a failure mode and then you're running not on something, you can check if something's failed. And that's where you'll primarily see, like, you would think, oh, why is if 12 even a thing? And that's the main reason, is the fact that functions that return non-zero things, it can be used as an error code as well, and you can just check if it's 0 or not. Anyway, we'll go into that a bit more in the functions section. Okay, now here's the fun part. I question if any of you have seen these operators before. You almost never use any of these in the programming that we do outside of. I wonder if they took this out of the 333 curriculum, because this used to be, back when 333 was a C class, these were interspersed within the 333 curriculum. Now they might be in the 404 curriculum. I had to use them in 404 quite a bit because, at least for us, 404 was also in C. I know this semester it was in Java. And Java actually also has these, but they're nowhere near as fast. In C, the bitwise operators are exceedingly fast. So what are the bitwise operators, you ask? The bitwise operators are basically operations on the raw binary of the representation of a number. So essentially, unlike the logical and an or, oh my god, it's going too fast. Wait, okay. Unlike the logical and an or, this is the and an or on the bits of different numbers. And it essentially goes through and combines if you have two separate numbers. And this is going to be very hard to visualize without the proper... I wish I had pulled up a addition table to help show this off. But I can actually go absolutely insane and just do this in the console, the JavaScript console in F12. Oh boy, let's take a try at this. If I do, where is my 60? What is it? That is the right thing. Okay. What were the okay. 60 and 13. So we're gonna say 60. We're gonna convert that to binary with toString, and we're going to convert that to base 2. Okay, so there's 60 in binary, and now we're going to convert 13 to binary like this, and that's that number. Okay, and that's going to get pushed down a few decimal places. So now what we're going to do is we are going to actually add these numbers and view what their result is in binary. No, we're going to AND these two numbers and view the result in binary, and then I will hopefully be able to talk a bit more about what's actually going on here. 13, and we get, is that what they wanted? Yes, okay, good. So you're probably wondering what the hell was the result of that operation, and to show you that, I will pull up MS Paint. So if we actually take a look at these representations here, we see that we're starting off with 1, 1, 1, 1, 0, 0. And then the number we have under that is 1, 0, 1, 1. And the result and the operation we are running on it is the ampersand operation, which I cannot draw. Yes, that is an ampersand. You are welcome. So we are going to fill in these empty spots with zeros. We're going to pad that. So what's actually going on in the AND operation? Well, much like the logical AND, we're performing this bitwise on every single bit. And that's why these are called the bitwise operations, because we're going down on every single bit. So 0 and 1. Well, what's the result of that? Well, they're not both 1, so it's 0. What's the result of the next one? 0. This next one, 1 and 1. 1, that's true. 1 and 1, that's also 1. 1 and 0, nope. 1 and 0, nope. And as you can see, that's the result. We get 1, 0, 0. And you're probably thinking, well, why in the world would you do this if we're just working with numbers, right? But the thing is, you're not always just working with numbers. You, especially at the hardware level and the operating system level, working with the individual bits, manipulating individual bits is extremely important. And especially, you're going to see this a lot in the operating system development video, that there's stuff like the, oh boy, let me, I'll pull this up just for comedy. Let's pull up the global descriptor table on the OS Dev Wiki and take a look at this. Basically, these are bit offsets into the global descriptor table at these incredibly weird things where you have to manipulate bits 52 and 53 with bits 55 through 52 with your bitwise operators. You're actually like going in and trying to edit individual bits inside of numbers that are being represented by ints. And that's why these bitwise operators are so handy, especially at the low level. So this is, you should pray that you never see this in the field, but if you're working low level, you most definitely will, especially with these flags and everything. You're setting individual bits in these flags using bitwise operators. And you're also going to hear about masking, but that is, we're gonna just hold off on going too in depth with this for the workshop. Anyway, let's talk about what else we have here. There's a few other operators. There's the OR operator, which does the exact same thing as the AND operator, except now we're performing OR on the top and bottom essentially, instead of, I mean, we could just go back into here and do it and just erase all of this. Can I get this bigger? Is the question. Oh, that's not that much bigger at all. That's very unfortunate. Actually, that worked better than I thought it would. Okay. So now we're going to be doing bitwise OR, which is just a single downstroke. Anyway, so is 1 or 0 true? Well, yes, we have a 1. Good. 1, 0, 0. No, that's the only thing that's going to be false. 1 and 1. Yes. 1 or 1. 1 or 1. Yes. 1 or 0. Yes. 1 or 0. Yes. And let's see if that's the right result. And look at that. Yes, it is, question mark? Yes, that is correct. They're just padding it with an extra 2 zeros at the end, which of course you can legally do. That's like saying 600 and then just putting zeros here, but you would just ignore those, but we still can keep them in the representation if we want. Anyway, then XOR, this is another one, except you're performing the XOR operation, which is the exclusive OR, which basically just means you're ignoring the case in OR where they are both true at the same time. In that case, it's 0. If anyone wants to post the truth table to that, I saw someone posted the AND truth table. If you want to post the XOR truth table, since that one's a bit, that one's at least not as straightforward as the AND and the OR. But anyway, we offer XOR capability, and then this one's interesting. This is the binary ones complement. So the binary ones complement basically just flips every single bit in the number. It basically just inverts it. So if you're a 1, now you're a 0. If you're a 0, now you're a 1. And this was actually a problem we had last night at the coding practice, for coding practice night. We actually programmed this ourselves, which was very interesting, especially to do without the bit flip operator. Anyway, next up we have the binary left shift operator and the binary right shift operator. And in C++, you might recognize this as the stream operators, but in reality, they're just overloading the actual the bit shift operators. So what the bit shift operators actually do is they take your number and they shift all of the bits over by 1 and add a 0 on the end. And I'll do a demo on why we might want to do that. So let's, you know what, when in doubt, start with the MS Paint demo so you can draw it out. So the first thing we're going to discuss is, let's see, we have 1, 1. Let's just say we have 1, 1. And then we run shift, let's say 2 on it. What this actually does is pushes these 2 bits down another 2 places and pads it with zeros. So 1, 1 in binary, shift 2 is going to be 1, 1, 0, 0. And we can actually, again, I don't like using JavaScript for this since everything's represented as a float, but I can at least pretend it's not. I can quite literally do 0b, which indicates that I'm typing a binary number, 1, 1, shift over 2, and as you can see, we've shifted 1, 1 over 2 bits, so now it's 1, 1, 0, 0. And of course, I'm sure you can guess what shift right does. It's the complete opposite, right? If we have 1, 1, 0, 0, 1, and now we shift it over 1, it's going to take that final bit into the void and just delete it and push everything else to the right 1 bit. And this is very interesting because you can use the bit shift operators in conjunction with the with the logical and or logical or operators to get different bits within a binary number. So let's say this is the most practical use I can think of, and I do this quite a bit with a lot of bit manipulation. I'd open up my operating system code and show you some of the actual practical uses, but I think it'll be better to do it right now. So let's say I want to get, let's say I have the byte 11001100, and yeah, okay, so that's a byte, right? That's 8 bits right there. Let's say I want to get this bit right. Can I increase the size of this by any chance? I think I can. Oh yeah, look at that. Beautiful, beautiful. Okay. So let's say I want to get this bit right here. How do I go about figuring out whether that's a 1 or a 0? Now, normally, we don't have, actually, I'm not shifting it, I just want to display it. So how do I go about extracting this? And this is, you almost never have this issue because normally this is quite literally just the number 204. Why would I care what the 7th bit of 200, or I don't know if this is, I guess you would refer to this as the 2nd bit. Or maybe this is the 2nd bit. No, this would be the 2nd bit. Oh well, we'll just call this the 7th or 6th bit. Sure, why not? How would we get this is the question we want to ask. And I mean, normally you don't even care about like why would you want what that bit is. But there's actually a lot of reasons, and that being, let's say I actually wanted to extract what the flag was. These flags represent different things that the processor can do, and they're all 1 bit. So clearly I have to extract these individual bits from stuff somehow. And the way that we go about doing that is with the shift and bitwise operators. So I'm going to go back into my Chrome console here and actually show you that the operation I would take to getting whether this bit is a 1 or a 0. So what I'm going to do first is I'm going to say, okay, I want this bit, right? So what I can do is I can shift the entire thing down to the right, however many places I want to delete off. So 1, 2, 3, 4, 5, 6. Okay, so let's shift this over 6, and I want to see the actual result. So I'm going to string it as a binary number instead. Number dot toString base 2. Okay, so what I've done here essentially is I've taken this number down and I've cut off these 6 decimals by shifting it to the right 6, right? I've cut off these 6 digits by shifting it over, right? And now I just want to extract this one. So how am I going to extract this single bit? Well, quite simply, I just want the thing on the end. So what I can do is I can say, oh, ignore every other bit by running an AND with 0, B, 1. And we are now able to extract that individual bit by shifting and then ANDing with the thing right on the end. And that what we're doing here when we AND with 0, 1, 0, B, 1, this is actually 0. This is 0, B, 0, 1. And that extra 0 is ANDing with this 1 right here. And we're getting just this 1 in this position. And that's really why you would want to do this, why you need these operators, because you want to be able to extract individual bits. Sometimes you even want to be able to extract multiple bits. Let's say I want the bottom 4 bits here. How am I going to cut off the top bits? Well, quite simply, I'm going to AND with 0 with 1, 1, 1, 1. And this is going to give, they don't like me. Oh, it's because I have the thing left over. So this is extracting the bottom 4 bits because we're ANDing with 1, 1, 1. I'm pretty sure this is what they call masking. I actually don't know the terminology behind it. I just know that I use it quite a bit. And what this actually is 0, 0, and we're basically just stacking these on top of each other and using this to extract these final 4 bits. Or we could take this and we could shift these 4 bits up to get the top 4. So if we shift this up 4 bytes, and then, of course, we're going to have to shift this back down afterwards, which is not going to be very pretty. There's a more elegant way to do this. Now we're getting the top 5 bytes, which we can actually see because they're all the same. Can I fix that? Uh-oh. Did they not like that? I can't really tell what order of operations is going on right here. Let me... Okay, there we go. So this is extracting the top 4 bytes in probably the most roundabout way. A much easier way of doing this would be to shift this down first and then by 4, and then ANDing with. And normally you're going to see people use hex here for their masks, 0F, which 0xF is just 0B1111. 0B1111, same thing as 0F, right? Because text corresponds to binary, the 4 digits of binary, right? So anyway, that's enough for the bit shift operators, which I know this can seem very overwhelming, but the better you get with bit shift operators, the more comfortable you become with binary. And by the end of it, you really feel like you've mastered binary. You are the master of individual bits. And that's one of the reasons C is such a great language, is because you have this raw access and power over the individual bits, and everything is a number. So you can literally just manipulate and twiddle anything you want. It's actually it's quite powerful for these low-level features. So finally, let's take a look at the assignment operations. So the assignment operations are the actual equality, right? You're setting a variable on the left-hand side to the right-hand side, right? C equals A plus B it's making the result of A plus B in C. But then you have these other magical operators, which basically have they have an operator and then they have the equal sign after them. And the reason that we have these is because it's all shorthand, and I do believe I showed this off earlier. Not that, I want this. Yes. I showed off earlier that if A equals 10, A equals A plus 1 is the same thing as A plus equals 1 is the same thing as A plus plus. But here we could also do A equals A plus 10. And in that case, now we're saying, okay, so A equals A plus 10. This is equivalent to saying A equals A plus 10. You can instead say A plus equals 10. It's basically just shorthand because, especially for accumulators, this is like very common that you're writing a assignment in this syntax. So they basically just include it in with the language. Oh, we'll just make that a thing by default. Also, why do they? Okay, yeah, I that was my mistake. Was compiling to binary. But we can see here that essentially, again, it's the exact same thing. Look, we are adding 10 to A, and this is also adding 10 to A. In the assembly, both of these lines compile to the same thing, but this is just shorter and more concise, right? Looks nicer. All right, so back to the actual presentation here. And this is for every single operator, essentially. They have any operator that takes in 2 operands, except I don't think there is a logical AND assignment. Is there? Let's, whoops, let me, okay, I'm going to X out of that because that's confusing. I want to use this one. Okay, so I don't believe, let's check this out actually, because I'm not sure if this is a thing. So if I say int A equals 1, is A and equals 1 a thing? Is this not a real operator? This is not a real operator. That is so sad. I wish that was a real operator. Anyway, back into it. So essentially, all of these operators are basically just the same as the thing equals the thing, that operation, and then the thing after that operation, right? And it's all just shorthand for the rest of these assignments. Primarily you're going to be using equals though, right? That's the real thing you're going to be using on every statement. And now, finally, it's probably the most exciting part of this presentation: operator precedence. So operator precedence, this is PEMDAS for the C programming language. Except instead of PEMDAS, there's 15 different steps, and they are all evaluated in order. So basically, we're not going to go over all of these because these are extraordinarily well, we've gone over every operator already, right? So, but really, you do have to pay attention to this because there's things, especially when you're doing bit shift operations. You see here that bitwise shift left and right. You're normally also working with bitwise operators in here, right? Like bitwise and bitwise or. So you always have to keep in mind the precedence of your bitwise ands, your bitwise ors, and your shifts, and when you need parentheses within there. You saw that I got tripped up in the JavaScript example I just did because I didn't add the parentheses up here. It basically got the wrong ones that I didn't want because I thought that the precedence was in the other direction, and clearly it is not. And I had to add parentheses around where was it? Oh, I think I edited the actual thing. Unfortunate. But you actually have to pay close attention to the precedence. Personally, don't memorize this. Just always when you're working with this stuff, look it up because you really won't regret it. If you can have some really weird bugs caused by not paying proper attention to operator precedence. But here's some good news: is the fact that PEMDAS is actually maintained across C operator precedence. So we can see that parentheses are the first thing that are evaluated somewhere in here. Where's cat? See, I feel like parentheses are I don't want the function call. I want just like normal parentheses. Where are my parentheses? I know it's not the compound literal either. It's not the cast. But I do know that parentheses are the first thing evaluated. They might not even consider parentheses as operators in this. Anyway, so yes, parentheses are evaluated first. There's no such thing as exponential in C. You have to call math.exp. Well, in this case, it's just import math.h and then the exp function. So that's you don't even have to worry about that because actually it is a function call. So technically it is the first thing of operator precedence. M, multiplication down here. D, division is right after it. Yeah, so multiplication takes precedence over division. And then addition and subtraction, PEMDAS. Yes, so that's PEMDAS. PEMDAS is maintained in C operator precedence. Okay, so we're going to continue. There's also some other interesting operators like the comma operator and the ternary conditional. But I am not going to talk about the ternary conditional because that is beyond the scope of what we're doing, as well as the comma operator, which actually got removed from C++ recently because they didn't think it was necessary, which was very sad. Anyway, now into the actual control structure of C programs, right? So the first thing we have to talk about is conditional structures. And conditional structures, I'm sure you're well aware, especially those of you who have taken Java, which I'm sure most of you have. It's essentially the exact C influenced control structures in Java in the sense that literally Java basically just copy and pasted C's control structures, except like try, catch, and everything that doesn't exist in C. So the first thing we have, of course, I'm going to go through this very fast since I know everyone probably knows these already. So the first thing we have is the Boolean expression, right? If statements. This is the most basic control structure you have, right? If this is true, but not if this is true, if this is zero, or if this is non-zero, right, then this statement's going to be evaluated. Boolean expression just means non-zero in this case. So essentially, then the statements inside of your if statement will execute. This is pretty straightforward. Let's take a look at this sample program right here. Okay, we declare our a variable to be 10. If 10 is less than 20, which it is, then we print that a is less than 20. And then what's this doing? Its value of a is 10. Okay, so yes, we are going to get from this that yes, indeed, a is less than 20, a is 10, right? So this is it's going to trip this conditional statement, right, and go into the if block. Otherwise, we're going to skip that. For example, if this was 30, this statement would not trip. I feel like everyone basically understands the general idea of if statements, right? If else, same thing, except now we have code that's executing in the case that it's not true, right? If it's false, then we're going down to the else block and executing that. So now a is 100, a is larger than, or is 100 less than 20? No, that's false. We're jumping to the else block. And of course, if a was less than 20, if a was 10 here, we would execute this, but then we're jumping over the else block. We're not going into the else block. First we check this thing. If this is true, we go and execute this code. Otherwise, we're executing this code, but we're never executing both of these at the same time, which you could do with a switch statement. But I skipped switch statements in this presentation for brevity. But that probably wasn't a good idea, since we might use some switch statements in operating system development. Because for those of you who don't know, the switch statement is actually one of the most powerful statements in the C programming language. And it's because you can do lookup tables and jumps that are much faster than if-else chains. But I am not going to go into how that works today. Maybe I'll go into that tomorrow. And that could be an interesting thing to see how that works in assembly. All right, so next we have the if-else-if block, right? Where we have lots of else-ifs, and we're only executing one of these code blocks, right? We have our first Boolean expression, our second Boolean expression, our third Boolean expression, and it basically just goes down this chain and checks, all right, is this true? If it is, do this. Is this true? If it is, do this. Is this true? And if it's not, you finally get to the end, and then you run your code in the else block, right? So that's the if-else statement. I'm sure you're all familiar with that. Next, we have to go over loops, and I'm going to just be going over while loops and for loops, which are the two loops that were introduced by the C programming language and have been, again, copied into literally everything else. All right, so first up, we have while loops, right? So the while loops, again, it takes a condition, and in this case, condition is a Boolean expression. While loops will only stop when the condition evaluates to 0, right? So until then, it's going to repeat all of the statements within that block. So here's a quick little example. Basically, we're saying, all right, a is going to be equal to 10. And then we say, all right, while a is less than 20, we're going to print the value of a and then increase a by 1, a++. So we're going through, and as you can see, the output, we're printing out, okay, a is 10. All right, now a is 11. Now a is 12. Now it's 13. Until we get to 19. And at that point, we trip it because now a is 20, and the second a hits 20, this loop stops because this expression all of a sudden evaluates to 0. And once this expression evaluates to 0, we jump on out, and we return from the program, and it ends. Next up is for loops. And for loops, when I first learned programming, I could not figure out for the life of me what the point of a for loop was, because I said, you can do this with a while loop. And yes, you 100% can do everything you can do in a for loop, in a while loop, because they are for loops in the C standard, at least in the C++ standard, I don't know about the C standard, are quite literally defined in terms of while loops. It's exactly equivalent, essentially, to writing this, except for the fact that I has a local scope inside of the block here. So this actually isn't exactly the same. You would have to add another block around here. So I didn't have scope within the rest of the function. But essentially, it's the exact same thing. But this structure was so commonly used that they felt the need to give it its own thing, right? Called the for loop. So primarily now, best practice is you use a while loop when you don't know how many times you're iterating your code for, and you use a for loop when you know exactly how many iterations you're performing. So that's the general idea behind while loops and for loops in modern programming. Of course, there's also edge cases to both of those, but that's the general rule of thumb, right? So for loops, on the other hand, as opposed to while loops, you declare your initial step, which is the first thing that's executed once, and then you have a condition that's evaluated after every single loop, and then it stops basically if that condition is false. And then finally, you have your your increment statement, and your increment statement basically runs after the code in the loop has been executed, right? So essentially, what we're doing here is we're saying, okay, we have our variable I, which is just an integer, right? We're declaring it, we're setting it to 0. This runs once at the start of the loop. Now, in here, we're going to run our code. After the code is done, we do I++, which adds 1 onto I, and then this checks essentially every time before we start the loop. We're checking, okay, is I less than n? And then if it is, we keep going. If I is less than n, we keep going. But when it's not, and I finally becomes greater than or equal to n, we're going to stop the loop, right? I'm sure everyone is familiar with for loops, so I shouldn't be introducing any new concepts here. I just want to show the way that C does it, and I'm sure you guys already know the way C does it because it's basically the exact same as in Java. All right, so this is where the C language really gets to shine, right? Functional programming, and C is widely considered one of the most prominent functional languages. Which, of course, the Lisp people are going to come after me for saying that because Lisp is also is considered more functional than C, if you can say that. But this is C is widely considered one of the founding functional languages. So let's actually go into what functions are, because this is people often get tripped up a lot on just function conventions and when to use functions. Why do you? Lisp is not the god language. I disagree with that statement, Braden. I'm not a Lisp connoisseur. I've read an entire book on Lisp, but I can't get into it. Have you ever seen a Lisp program? All right, I'm gonna go on a tangent and pull up a picture of a Lisp program. Observe the pain. Observe the pain. Where is it? You see how many parentheses there are? Are you in as much pain as I'm in? I just see so many parentheses. I can't. It's too painful for me. I just can't. Anyway, enough about yes, Lisp. All right, let's pull back up the presentation and go back into functions in C. As much as I would like to go over functions in Lisp right now, because that's a hilarious topic. And Lisp is a very interesting language in its own right. I would love to get a presentation on Lisp later in the semester for anyone who wants to do a presentation on Lisp. Keep that as a potential workshop idea. Anyway, going back in. All right, so how do you define a function, right? So first, I think what's appropriate to consider is what is a function in general. What's the concept behind a function, right? So we can think of it more as a mathematical function if we want to. We can think of it as a black box where you put something in and something comes out. Or you can put some things in and get some things out, right? So for the basic general case, I'm going to create a function. You might be familiar with math, where we have the function plotted on the graph that just looks like the straight line, f of x equals x, right? We can perfectly represent this in C by doing essentially the function object, right? We're putting in this x and we're returning x. We're getting x out of this function, right? So we can model this in C by doing a function that looks like this. We're going to call it f. This first value is the return value, not the return value, the return type. This is the type of what we're returning. Well, if we're taking in x, and let's just assume x is an int and not a floating point number, then we are taking in an x. We are putting out an integer, of course, because we're returning x. And quite literally, all that we're doing for processing-wise is going to be return x. And lo and behold, we have perfectly modeled f of x equals x as a function in the C programming language. And now what we can do is actually input things. And all right, let's do return f of 5. So this is just the identity function, right? It's returning itself. So the program, as you can see, the program here has returned 5. And that is because what we are passing into f is 5. And 5 is spitting back out, and f is spitting back out 5. And that's what's being returned, right? So that's relatively straightforward, right? If we want to think about functions like black boxes like this is a good way of thinking about it. But functions can get much, much, much more impressive than just the identity function, right? So everything that you implement in the C programming language, all of the libraries, it's all functions. And forgive me for skipping ahead, but I would like to skip ahead to strings, where we see that every single thing in the string library, it's implemented as a function, right? You're putting things in and you're getting a value out. And that's all functions do, especially when you have, more advanced types like pointers and everything, which, believe me, we will be getting into later. This is essentially the root of how functions, though. I want to give some simple examples of how functions work before we get into, the real meat of what we can do with functions. Another thing to do, we can think about a very simple operation, right? The identity function, that's great. But you know what's also a function? Addition. Addition takes in two numbers and spits out another number. So we can actually just write addition ourselves. We can say, oh, int add, take in num1, take in a num2, and this also has to be prefixed with int, take in num2, and return num1 plus num2. And now we can say, oh, well, what's 5 plus 10? And we're actually going to return, oh, I renamed f to add. And as we can see, the program returned 15. We have created another black box where now we're taking in two numbers and we're combining them and returning the result of that. And the result of that is an int, and that's why we're prefixing it with the return type of int, right? So this is interesting. This is how we build, essentially, more and more complex functions. But you can think of this even as even in more abstract terms, where we could literally be taking in strings and doing operations on strings, or we could be taking in stuff and not returning anything at all. And in that case, it's called a void function, right? So, for example, if I just wanted to print out some value that I formatted, if I did print, let me include stdio, hashtag include stdio.h, which is input output. So I'm going to call printf, and let's say hello. All right. So for example here, I don't really care about returning anything from this or even taking anything in. So I can take no parameters or whatever. I can just call this function say hello. And we can quite simply call this with no parameters in main. And give me that. Goodbye. Get rid of you. I think that's going to default. Okay, I don't like that. I'll just return 0. And they don't like the fact that I don't have a terminator there. And as you can see, we're printing out hello. And this in its own right is a black box, except we're saying, oh, okay, call the black box, but we're not putting anything in and we're not getting anything out, but we're still calling it. And what's the reason you would want to do this? This is potentially for, say you had like a crap ton of code in here, like you had some really complex logging software that was doing some magic or taking stuff in, let's say, takes in A, which is the number, and then we're figuring out how many times it, we're going to do, we're going to print out, let's actually just print out all of the A and its subsequent numbers. So it's going to be A plus 1, and we can just print out like A plus 2, A plus 3. So this could be like a very complex piece of logging software in this function, right? And a very complex piece of functionality, right? But we might not, if we didn't have the ability to call functions, we would have to basically put this in every single time. So one of the main reasons that we use, like say I wanted to say hello 2, and then I wanted to say hello 3, sure. And of course I forgot to put in new line terminators here, but I can do that right now. One of the main reasons you would want something like this is because of the fact that essentially without this mechanism to basically compress code and have it be reusable with new parameters being passed in, you would have to rewrite these instructions every single time. So instead of being able to just be like, oh, say hello 2 and say hello 3, you would literally have to be like, okay, print all of these, set A here first to int A equals 2, and then down here you would have to say int A, or A equals 3. And this performs the same operation as the last one. Of course, I need to include semicolons. But this is the exact same operation. But look at how ugly this is. We're basically reusing instructions that we could be putting into this say hello function. And this is one of the main reasons for functions, is the fact that you can modularize and put code that's being reused into these tiny little modules called functions, and you're able to actually reuse that and get, really good reusability out of your code. And the fact that you're able to declare your own and everything, and the fact that the libraries provide them to you like that, make really the function the base of the C programming language. All right. Next up, let's discuss after does everyone understand? Does anyone have any questions about functions? Once you've learned like Java methods and everything, functions on their own should be pretty straightforward. I mean, yeah, you could consider. This is another thing that people coming over from Java don't often realize, is the fact that quite literally with functions, you can declare them just like inline, right? Like, like in Java, everything has to be inside of an object. That's very restrictive. That doesn't offer you the same freedom as just the C functions that are free floating around in your global namespace, which some people would argue is a bad thing. But it can also be quite the blessing in many cases. Okay, so let's get back into it. We're going to now go from functions into arrays. So for those of you who, I assume everyone knows what an array is, right? It's just a contiguous section of memory with different values in it, essentially, right? So you have your first element at 0 and your last element at whatever your array size is. In C, we can declare arrays using the type, the name of the array, and then brackets, and then the size of the array. And what this is actually doing is declaring a contiguous chunk in memory on the stack. So we can actually see that going on here when in main let me get the assembly view up, we actually declare an array. Let's declare an array and see what's going on here. So I'm going to say, okay, this is an array of size 10. And now let's take a look at what's actually going on here. Oh, they actually don't care because I'm not using it. I'm not even optimizing, and they don't even care. Okay, so let's fill it. Sure, why not? Let's create an array of size 3 and see what we can get. So to assign to an array, after we've created this array here, right, we're going to actually access it using the braces as well. So a sub, this is sub. You say sub when you see these braces here. You don't say a bracket 0, you say a sub 0, which is the element at the 0th position of this list, right? So, and we can assign to this as well. So I'm going to just put 1, 2, 3 in these positions. So 1, 2, and this is going to be 1, this is going to be 2, and we're going to say 1, 2, 3. Now let's actually take a look at what's going on here. We see that what's actually happening is that this array has a spot in memory that we can't directly observe. It starts at -12 from the register base pointer, which is not the register base pointer, the base pointer, right, on the stack. And then it's counting basically every 32 bits or every 4 bytes. It's adding a new int in here. And that makes sense, right? Because we have declared that this is an array of int3, and therefore every 4 bytes or every 32 bits, we're going to be pushing our new value, or in this case, moving our new value into this memory location on the stack. So essentially, that may not have made that much sense to those of you who don't know x86 assembly, but essentially what's important to see here is the fact that each of these operations is performing on this same contiguous chunk of memory, which is A. And when we get over to pointers in the next section, we'll see that essentially arrays and pointers are one in the same thing. And that is where things in C can get very interesting and also very complicated. The number one thing that trips people up in C, they can normally get functions down and everything fine, but when it comes to pointers and arrays and the relationship between pointers and arrays, things can get very confusing very fast if you're not careful. Also, I should point out that you are not allowed to dynamically decide the size of this array. So for example, if I say, this might be an issue, but I'm going to test this out. If I say in size equals 3, and then I say size here. This might work, but I don't want it to. Okay, so this successfully compiles because it can automatically tell we know this at compile time. But let's say I was passing this in as a parameter instead, int size. This is now completely illegal. And of course, they're not telling me that it's completely illegal, which is a major issue. This should not be legal. What the heck are they doing? I don't understand why this would be allowed. This isn't allowed. Apparently it compiles though. This is a you're not allowed to know. Actually, it probably knows the size at compile time. I kind of understand what's going on here because it thinks I'm passing in probably command line options, and it's just taking that and declaring it as if it's okay. Yeah. So essentially, never do this because this is going to break your program. I'll say that right now. This is not something you should do. Even if this compiles, this is going to cause a hell of a runtime error if we ever actually try and execute that. Moving on, though, let's actually talk about pointers. And pointers are lots of fun, and the number one thing people get tripped up. I just talk about how you can basically you can say equals and then afterwards the concentrated list of values that you want to put in your array. Of course, they all have the same, right? Like you're promising double, and here are all of the doubles that we're throwing into our balance array here, right? We did something. We did casting. Of course, everything is numbers, so you can cast everything else. But we are theoretically, stop. Let me show all. Let me pull it up. Talk about a magic trick that I have that this is very useful to other people who have, and I hope this will be very useful to everyone who's using C from now on. This is quite a cool trick. On almost all compilers, this works. If you declare an array of size 10, this array is not guaranteed to be zeroed out at at runtime. So if I do print, let's actually do a printf here. If I printf and then I print out, let's print out the number, and we're going to do new line, and the number we're actually going to be printing out is going to be a sub 0. Let's actually see what comes out here. I'm curious. As you can see, we get negative 52,000. So we declare this array, right? But just because we've declared this array doesn't mean anything about what's guaranteed to be in it at runtime. So what you actually want most of the time is to set everything in this array to 0. So we could do that with a for loop, right? We could do int I equals 0. We could do I less than 10, because that's the array size, I plus plus, and then we could do a sub I equals 0, right? And then we've zeroed out everything in it, and as you can see now, if we go through every single thing in it, we're going to get all of these zeros, right? This is boring. This is not. This is long. You don't actually have to. Thank you for your analysis, Connor. I agree with that statement. I feel like if people treated pointers more like poggers, we would have a much nicer society. Anyway, so yes, you can run this simple algorithm to clear your array and guarantee zeros across your array, right? Rather, what's very interesting is the fact that instead of that long for loop, you can do equals brackets 0, and that will guarantee 0 out the entire array for use on things. So now we can see going through here that all of these indices, they've returned 0. Even though we've only said equals bracket 0 for the first element, and there's 10 elements in here, most C compilers recognize this little hack right here as meaning, 0 out the entire array. And that is a very useful trick. All right, so moving on here, let's actually talk about pointers. And pointers, this is where everyone, I said that, I think I said this already, but this is what makes and breaks people who want to become C programmers. They hear pointers and they think that like this is the end of the world, right? And back when I was in high school and I was learning C++, my teacher was like, "Oh yeah, we don't teach pointers in our class. That's college level stuff." So this is what, like, this is, pointers are widely considered like Satan in computer science terms, and they go to great lengths to avoid pointers. Pointers confuse people a lot, but you really shouldn't be confused by pointers, because really all pointers are pointers to memory locations that store your variables. And if you think about this in terms of assembly and memory locations, it becomes a very intuitive and not as scary as they make it out to be. You know, the people that pointers really scare are people who main Python and JavaScript, because they never have to deal with a memory location in their life. And I mean, Java as well. But once you master pointers, you will be an incredible C programmer. No, a incredible C programmer, because C is not a val. Okay. So let's actually go over pointers. So what is a pointer, first of all? Let's take a look at let's do some definitions here, right? So how do we declare a pointer, right? A pointer is a type of variable that we declare, right? So we have to declare what we're pointing to, and essentially what we're pointing to is the type, and then we follow it up with a star, and that star says this is a pointer. This variable name is a pointer to a type. And this is something that people actually don't understand very well, and it constantly falls through. C types are actually named backwards. And you see this with more complex C types. There's something called east const versus west const, which is actually a big debate within the C and C++ community. You can say const int a equals 0, right? And this declares a constant, a zero constant, which means you can't change a after it's been declared. However, this is semantically equivalent to int const a. And they don't, because it's renamed. Okay. So these basically do the exact same thing. They're declaring the exact same variable here. I mean, I can just, yeah, they quite literally declare the exact same thing. This is called east const, because if you think about the screen like a compass, it's north, east, south, west. So there's west const, which is what you normally see, this, and then you have east const. Now, here's where things get really confusing, though, because what if you have a const char pointer, which is what is normally a string in C? So you have const char pointer. You have to think about what this is really saying, because normally you're supposed to read C types backwards. So now we have to jump around a bit. This is a pointer to a constant character. So we're going left side, we're going all the way right, all the way left to the middle. So people argue that east const is easier to read, because now we can just read this entire thing backwards. This is a pointer to a constant character. And you just read the type backwards to know what the thing is. So if we call this A, and then we put a string in here, we know that A is a pointer to a constant character. And this gets even more apparent when we have function pointers, which maybe I'll go over at the end if we have time. Right now we're getting up to 1 hour 40 minutes, so I probably won't have time to go over function pointers. In fact, I probably won't even have time to go over installing your own compiler. But this is going to be fun. So anyway, let's actually take a look at what pointers are doing here. So I've told you how to declare a pointer, but I haven't really gone over the intuition behind what a pointer is. And a pointer is a memory location. It is quite literally just a number that represents a location in memory. So I'm sure you are all aware that computers have something called RAM. And in that RAM is where all of your program variables and everything are stored, right? So we are able to actually access the locations in that memory and index into it with a pointer. A pointer is an index into RAM of where your memory is stored. So we can actually go through this and create a pointer into, okay, hang on, let me expand this out here. We're not going to look at the assembly behind pointers, because we will be in lots of pain if we do that. So instead of that, we are going to do something very simple at first. We're going to say int a equals, we'll just say int a equals 0. And you know what, for the fun of it, let's say int a equals, what's a fun number? 100. 100 is a fun number. Okay, so we're saying int a equals 0. And now let's say that for some reason we wanted to know where a was stored in memory. So for this, we would use a very special operator This is not the bit shift operator. This is the memory location operator. This operator returns the location of where your variable is in memory. So if I say int b equals a, this works, but you should not be doing this, because this returns, essentially, this operator on a returns a pointer to an integer. So we're going to say that this is an int pointer to b, right? So this is how you normally would declare a pointer to a variable, right? So now we have a, and now we have the location in which a is stored represented as b. But we shouldn't be intimidated by this notation. We have to keep in mind that this is just a number as well. And we can see that by printing it out. Quite simply, if we run printf, and then we do, I don't know if this is a 32-bit system that they're running this emulator on, but we sure as hell can check. Let's b, and let's print it out as if it's a decimal. And as you can see here, we get this really big number. Now you're probably thinking, why is this a really big number? Well, that's just a pointer into the memory location. The operating system determines where this actually is in the memory. So we don't really care about what this value actually is. All we care is that this value is a pointer to the memory location that A is being stored in. And where this memory location actually is, well, it's actually, if we take a look at the program code, it is quite literally on the, where is it, yellow? It's on the stack at -12 to the base pointer on the stack. So this is in memory right here. And all this thing is doing right here is, it's actually, if we look at the assembly instruction, we're saying load effective address quad word. Okay, which means this is a 64-bit system since it's a quad word. But that's kind of irrelevant. And essentially all we're saying is, okay, find out what the look, it's literally saying right here, load effective address into RAX. It's what this is saying is, okay, what is the address of RAX? That's what the load effective address instruction does in x86 assembly. It's saying, okay, what is the address of this memory location? And to actually calculate this, it's literally just RBP -12. And that's all it's doing to calculate this address. And then it's basically moving that address into its own variable b, which b is represented by -8 to the base pointer on the stack. Again, sorry for the x86 talk. I just love talking about x86 assembly and its relationship with C, which we will be going over in much more depth tomorrow. Anyway, so next up we have, so essentially you can see here, right? This is just an integer. And we could actually cast this if we really felt like this. We could just treat this like an integer, and we could say, oh, okay, that's a since we're on a 64-bit system, it's going to be a long int b, and it's going to warn us, but it's actually the same exact thing, and we can cast any pointer to a long int if we're on a 64-bit system, because really what a pointer is just a long int. It's just an index into 64-bit memory. Right? So here we can see we've literally just cast the pointer into a long int, and it again, everything in C is a number. Even the pointers are numbers. We shouldn't be intimidated by that fancy pointer syntax. The reason we have the fancy pointer syntax is because pointers are different lengths on 64-bit systems and 32-bit systems. 32-bit pointers on 32-bit systems are 32 bits. Pointers on 64-bit systems are 64 bits. So all we're saying here is, well, we don't really care about the length of the index. We're just saying, okay, this is going to be the actual number that this represents is going to be the length of pointers on whatever system we're on. And then we read it backwards to figure out what it is. And this is nice because it lets us know that we are looking at a pointer to into an integer, right? So whatever this memory location is pointing to is an integer, and we can treat it like an integer. For example, if it was a float, we wouldn't want to accidentally misread it and be like, oh, well, now I don't know what type of data is being stored here. For all we know, it could, because floats are stored in binary a lot different than integers, in case you didn't know. Or if it was a signed integer pointer or anything, or a character pointer if we were talking about strings. Anyway, we'll get more into that in probably the next slide. So before I finish off with pointers here, let's actually say, okay, so now I have my thing, right? Like I have a pointer to that. What can I do with that? Well, one of the most important features of pointers is the fact that you can dereference them, which means we can take this B and we can actually have access to the memory location by doing this new operator. This is called the pointer dereference operator. And we are going to be doing star B. And now this directly gives us access to the memory location of A. So now if I say star B equals 10, and now we print out A, let's actually print out A and see what A is now. We see that A is now 10, despite the fact that we've never changed A. But what we are doing here is saying, get me the memory location of A, now dereference B, and now we have a direct line of access, a pointer, if you will, into where A is being stored, and we can set what A's value is through this memory address with the dereference. And that's what's so cool about pointers, is the fact that I haven't touched A. I said A equals 0, right? But what's really going on here is behind the scenes, we're dereferencing this pointer to A and saying, okay, we now have a direct line into A's memory location, set it equal to 10. And this is effectively similar to a concept known as references that you're using in Java. Essentially in Java, everything is secretly a pointer, but you just don't know about it. In Java, you have whenever you copy an object, you're not actually copying the object, you're creating a new reference to it, which is just a pointer without the need to run this dereference operator on it. Anyway, that's all you need to know about pointers, because it's quite simple, right? You can declare the pointer using the reference operator, using the memory location operator on a variable, and then you can dereference it to get a direct line of access into that memory location and set it. And essentially, we're setting A again without actually accessing A, because we could just do A equals 10. But what we see here is this is A equals 10. Star B is dereferencing to A, essentially. Anyway, to continue on with pointers, another interesting thing to note is the fact that arrays are quite literally pointers. When I say int A equals, or int A, let's say we're declaring our array of size 3, and we're saying 1, 2, 3. It's important to ask the question here, what actually is A? I said everything can be represented by a number in C, right? And instead of an abstraction. So what actually is A? What happens if we print out A? Well, we see that we get a really big number here again. Now, this is what's really cool, is the fact that A is a pointer to an array of integers. And now you're probably thinking, well, what's a pointer to an array? Well, a pointer to an array is simply the first address in the array. And let's take a look at what the first address in the array is. We can see it right here, right? We're printing out A, and this is going to be our first address at the array. But what's in the next address? So the cool thing with pointers is the fact that since this is a pointer, if I do A plus 1, what's at the next value? We get, this is, I see what's going on here. It's the fact that, so we would actually have to do A plus 1, and then in parentheses, give us a new pointer, and then dereference it to see what's in the next slot. And now we're doing some crazy, this just looks wrong, right? But we're able to use this to get the value in the second slot of A, because A is actually a memory location to the first value of the pointer. So if we take that memory location and then we do plus 1, and there's actually some black magic going on, we're not actually adding 1 bit, we're not actually adding one byte, we're adding 4 bytes, because it's an int and it's able to detect the fact that since this is an int pointer, when we do plus 1, we're saying, okay, go fetch the next int. So we're doing plus 4 bits instead of, or plus 4 bytes, my bad, instead of 1 byte. And this has actually caused me, this has caused me quite a bit of grief on my operating system project. I didn't realize that it was dependent on the type when you do pointer arithmetic. So yes, we're able to essentially access it like this. The same way we could say A sub 1, we're able to dereference A plus 1 and get the actual value at that location. So that's really the core of pointers. And when we realize that actually what's going on here is that the subscript operator is equivalent to accessing a location. A sub 0 actually just translates to, literally, it's defined as being, the subscript operator is, let's get it. I'll comment this out. So the subscript operator, if you do a sub n, is perfectly equivalent to dereferencing the location at a plus n. So these two things are exactly equivalent in C. And this is just shorthand for this, which is the longer version of how you would be getting the next consecutive element in that sequence, right? So this is essentially the core of pointers. And when we use these subscripts, we're actually just using pointers behind the scenes. We're using A as a number, essentially. Again, in C, everything, and I mean everything, is a number that the operators perform operations on. So, and I mean, you're probably wondering about like, what does this return? This returns essentially, C lets you, when you dereference things, that's why you're able to assign things like this, right? Because the only thing that's on the left-hand side is a memory location. Essentially, everything that's on the left-hand side of an equation must be a memory location. And you can either have the direct name of a memory location, like a variable, or you can specify that using a dereferenced pointer for the memory location, essentially. And that's why you're able to do magic tricks like this. And that's why this, when you're assigning a value to an array index, this is legal, because this is a memory index using a dereferenced pointer, essentially. Anyway, that's pointers can get very confusing, and I by no means believe that the explanation I just gave satisfied everyone. I think that you're definitely going to want to research more about pointers on your own, and definitely play around with some programs just to make sure you understand the basic concepts. And one of the ways you can do that, actually, is in the next slide, by playing around with strings. And strings are very important. Okay, so basically strings in C are pointers to arrays of characters that end with the null terminator. And the thing that's so great about ending with the null terminator, the reason all strings in C end with the null terminator is because we don't actually have to care about storing the length with it. Otherwise, we would have to store a length with the string. And that's just unfeasible, like, most of the time, right? We don't want to worry about storing the length with the string. We just want an array of characters, and we want to end processing on them when we've reached the end of the string. And we just mark the end of the string with the null terminator, which is \0, which in hex is actually literally just 0, 0, right? So let's do I think we can I can show off what's going on here, right? We have our hello, and then we have our null terminator. They're putting it in an address here. Yeah, so you do not place the null at the end of the string constant. Yes, so this the C compiler will automatically place a null terminator at the end of every string you make. So what we can actually do to demonstrate that is if I pull this up here, and we see that actually it's declaring this right here. But if we actually look at the binary, let's take a look at the compile to binary. Let's see it. Can I actually get the where is my declaration of the string? I just want to know where the string is declared. Come on. Are they not going to show it to me? I feel like they're not going to show it to me, and that makes me very sad. DSI. Oh, they're not going to show it to me, are they? There should be a memory location to where the thing is. Are they just storing it as... You know what? I'm not going to question it. I'm going to ignore that because that is too far in for the purposes of this workshop. So let's actually let's talk about strings for a second here. So we were just talking about pointers, right? So normally what you see is strings represented as const, char, pointer, and then let's call it hello. And keep in mind, this doesn't need to be a what don't they like? Why are they mad at me? Expected identifier before the... What? Have I gone crazy? Expected identifier or a parenthesis before the equals token. Do they not like the const? Char pointer. What have I done wrong? Have I made some really stupid mistake that I'm just not seeing? Does anyone... Is this equal sign wrong? No? I am beyond confused. Oh, I didn't put a name. I didn't name the variable. Oh my god. Okay. It's getting late. I'm going crazy. Okay. All right, so let's actually discuss what's going on here, right? So essentially, you can see that we have this string here in memory, right? And it's being stored as a constant character, or in this case, a pointer to a constant character, as we should now be saying, now that we are C professionals. And it is representing this array in memory hello, right? So we can actually go into this and get individual characters. What I think is going to be more interesting is to actually see every individual character in the array. Okay, so let's do print f, and we're going to show off that the final character in a string is actually always a null terminator. So we're going to print out each character not as a ASCII character, but as a number with %d. So we are going to print a sub, let's print a sub 0. And keep in mind that you can interchange even though this is a pointer to a constant character and not an array, you can use the index into as a pointer as if it was an array, even if you're not supposed to, which can also cause some serious issues as well. You're always able to use that shorthand for dereferencing at an index, even if this is a pointer. Like, this is an array, right? But this A just points to the first value, which means we're able to just jump values by using the sub operator, right? So, okay, so the first thing we're going to get is H, and now we're getting E. So that's 101 is the ASCII code for E. 2, we're going to get L. We should get 108. Maybe I was wrong about, yeah, I think I started at the wrong one. So 3, nope, okay, 3 is also 108, so that's another L. And then 4, we are going to O. And O is 111. But now, keep in mind, this is where things get fun. We get to show what the 5th character is. Now we are illegally exceeding the bounds of our array, and we see that it's 0, which means that the final character in this string is 0. But if we go beyond that, and we are legally allowed to go beyond that, even though we shouldn't, this is an out of bounds. Now we're getting 37, which means there's just random data beyond that 0 in data. And actually, what that 37 is, I think that's the percent sign stored in the %d\n. If we look in memory, the way that they store strings is in the data section of the program, and these are probably stored subsequently in memory. So after that \0, which is 0 in ASCII, the next thing that's stored in memory is this percent for the %d\n in memory. So we're actually reading into our own thing. So if I do 7, that's probably D. That's probably, yep, this looks like we're literally just reading into the next string that's stored in the assembly, which is this thing right here. Which is why you have to be very careful, of course, because if you exceed the length of your string, you're reading into memory that you really shouldn't be having access into. All right, let's I feel like everyone basically understands strings. We could go into the actual methods like string copy, string cat. I mean, we could kind of want to play around with string cat, but you know what? Let's leave that to later because we can actually demonstrate. We can, for the programming portion, we can play around and make our own versions of all of these, right? So finally, let's end off with structures. And this was basically object-oriented programming before object-oriented programming was a thing. And this is one of the main things that people seem to love about C, and it's also one of the things people hate about C and why they invented C++, because they thought this wasn't good enough for object-oriented programming. And to be completely fair, it's really not good enough for object-oriented programming. But what's so powerful about this is this allows us to extend the type system into more complex types that we can use for ourselves to represent complex structures, which if a language doesn't have this, it's not going to fare well, because this is what you really need, especially in the business world, to be able to define your own concepts basically as classes, or in C's case, structs. And in fact, you're going to see a lot of things represented as structs. In fact, you know what? I didn't want to show off the operating system, but I'm going to show off the operating system. See this thing right here? This is the GDT entry, right? So the way that you're actually going to represent this is by splitting this into different sections. So you're going to split this into, you see this is a 16-bit. Remember how I said you're never going to see a short? Well, this is actually a short. And this limit here, this is also a short. This is 16 bits, 0 to 15. This is 16 to 31. These are both 16 bits. And then you see all of these flags down here. The flags are the limit. This limit down here, 16 to 19, that's 4 bits, 4 bits, 8 bits, 8 bits, 8 bits. And we're actually going to see that this can be represented as a struct. And I will show that off in just a minute. But the first thing I want to show off, let me X out of that, X out of MS Paint, it's actually how you declare your structs, right? Because you want a structure that can store multiple different types of data, essentially, in it. Unlike an array, which only is able to store one type of data, we want something that can store multiple types of data. So let's actually get to declaring structs, and you know what, it would be helpful if I actually showed off the way that they show it. So the way that they're telling you that you declare a struct is you start with the struct keyword, then you follow it up with the structure tag, which is your name of the struct, and then you have members in the struct, right? And these are basically variables and widths of data in the struct, essentially, going down, and then finally you can end with declarations. But people rarely end with declaring a struct just in line like that, the way that they declare a book object here at the end after declaring the struct books. So each book has a title, an author, a subject, and a book ID, right? And the reason these are arrays is because that's the max length that they want for any of these. This is very common, you see this, because unlike C++ and Java, C does not have arbitrary length strings unless you are using malloc, and that is more painful. So essentially, here we have them declaring a single object, if you will, of type book, which is a struct of type books, essentially. And here you can see them suffering through and actually filling out the struct. Filling out structs in C is exceedingly painful, as you'll see in just a second. So let's actually go back in and declare our own struct. So, first person to type what they want our struct to represent. Give me any abstract concept, and I will write a struct that represents it. Just type it in chat. Node. What is a node? Node in like a binary tree or something? There's a lot of nodes. Linked list nodes. We got nodes for days. Node is kind of, you know what? Let's do lymph node, because linked list nodes are. I don't want to do a pointer to the struct inside of itself, because I don't want to confuse people yet. I could very easily confuse everyone by doing a pointer into the struct's type itself, and in that case, we don't want to confuse people just yet. I'll do a lymph node. Struct lymph node. Okay, so this is our struct lymph node. So what's some properties of a lymph node? Probably, lymph nodes are. I know nothing about biology. The lymph nodes have a size. Are they like continuous? Do they have like things on them? Let's do amount of lymph inside of it. I'll call this lymph. Lymph volume. Okay, so this is the amount of lymph inside of our lymph node, right? And we're gonna say, yeah, okay, that's an int. We're measuring the size of it, and we also want to name our lymph node, right? Like every lymph node in the body needs its own name, right? So we're gonna do char, and we're gonna say the maximum number of characters you can name your lymph node is something 100 characters long, right? So that's what we're saying about this lymph node struct. Now you have to end your struct. Like I could declare right here in line that I want a object, but that's rarely what you do. Normally what you want is to have the struct object, but then be able to declare objects of it later on in the program. So the way we do that is with struct lymph node and then the name of the object. So I'm going to say this is node 1. And now, congratulations, we have declared a lymph node, and I'm going to delete this because it's preventing this program from compiling. Okay, so now we have a lymph node structure, right? And we have an object of type lymph node named node 1. Now what we want to do is actually fill in this object, right? So the way that we're going to fill in this object is by directly accessing its members with the dot operator. So the dot operator, it's very familiar to people who do Java, where you're accessing methods and members with the dot operator. Normally, you're using methods. You don't have everything public though. This is almost as if it's a Java object, but everything, all of the actual private instance variables, they're all public, and which is terrible practice in Java, but that's the only way you can do it in C. So let's actually access our variables. So node1 dot name. Well, we can say you're actually supposed to, for strings, you're supposed to run str copy into it, and then we'll pass in what do we want to name it? Let's call it nodey. Sure. And then we are going to finish off with, of course, I have to import string. Include string.h. Beautiful. Okay, so as you can see here, here's something interesting that you might notice. There's no such thing as a struct lymph node in assembly language. It's basically just to help the compiler figure out where to store things. there's no, like, as you can see, all of these lines for declaring the struct and naming the struct and like declaring our struct variable, it doesn't exist. It doesn't translate into any assembly instructions. It's only when we start moving things into memory that the compiler starts saying, okay, now we're actually going to do some instructions. But the actual declaration and everything means nothing to assembly. It just gets optimized right out of existence. Assembly is only worrying about the bare bones operations that are going on. So if I then, let's finish filling out our guy. So I'm going to say node1 dot, let's get lymph volume, and we'll say that it has a lymph volume of 100. Sure. Okay. So congratulations, we have just declared our first struct. It is a lymph node, and we are adding things in. And as you can see, it is storing that struct in memory. However, it basically does not care at all about the actual structure of the struct itself. It's just using node1.name and node1.lymphVolume as locations on the stack to store these values at, without actually caring about the fact that there's a node object declared at all. It's basically just treating these as separate variables of type char 100, and type int, which is very interesting to see. So also, I should probably go over the fact that this is, if we actually look here, when they do the move-in, it's actually this right here. This is our big array of size 100 right here. I actually don't know why it's 112. What's under it? Oh, it's most likely. That shouldn't be 12 though. Why is it 12 and not? Because there's something on top of it. But what is this, the pointer? I have to figure out. I really want to figure out what that is, but I'm not going to waste time in the workshop doing that. Anyway, so yes, you see that essentially we have our struct declared here, and we can assign values into its members, which is what we wanted to show off. And of course, we can read these values back too. Yes, strings don't actually exist in C. 100%. Strings aren't real. It's just strings are an illusion made up by people who couldn't wrap their heads around pointers, essentially. Structs in, okay, so here, I'm very reluctant to compare C with JavaScript, because JavaScript is kind of demonic in the way, but yes, in the fact that in JavaScript, I hate the fact that I can literally just right click to pull up a JavaScript console at any time. But yeah, in JavaScript, when we have an object, everything in that object is public, right? You can say, oh, A equals 2. I'm going to declare this thing as being named, I call it struct A equals 2, B equals 3. Oh, they don't like that. What do I have to do? Do they really want me to do meme syntax? Okay, I'll do meme syntax. Sure. Yeah, but it's similar in the fact that you can just do now, I can just do struct.a, get the value of A, and I can do struct.b. Everything's public, right? But it is very similar in that regard, but I am reluctant to do that because, as you can see in JavaScript, we have this thing called the proto, which, since JavaScript is a prototype-based language, means with this struct, not only are we storing A and B, we are also storing literally every single thing we can do with it in there as well, and all of the variables that have to do with all of these different functions, which are their own objects, and that is the reason that my computer is currently using 18.5 gigabytes of RAM, because it is JavaScript. Anyway, enough memes about how bad JavaScript is. JavaScript is good, but the fact that it's a prototype-based language, while this is very useful, makes this a JavaScript object. This object itself, let's see if I'm very curious. Does anyone know how you can get the, can I literally get the size of an object in JavaScript? The estimated byte size of an object in JavaScript. Byte size of object in JS. Let's see. How to get the size of an object in JavaScript? Give me some funny hack. Oh, I can literally just do size of. Let's see. Okay, so if I do size of struct here, size of is not defined. They lied to me. That's another thing. Oh, it's a library. Oh, of course it's a library, man. I just wanted to know how to get the size easily. I don't want rough size of object. There's no way this is a thing. Size of. I'm going to attempt this. Let's try it. This probably doesn't contain prototype-based things. Unexpected identifier. Okay, they're never going to let me do this, so I'm just going to ignore the fact that that's the thing. All you have to know is that JavaScript takes up too much memory. Anyway, let's go back to C, which in this case, literally, when I say char title books, that's it. That's everything in here. Especially if I say attribute packed, then the compiler can't even optimize anything out. This is literally everything that's in here, essentially. And it's no bigger, no less. You're not getting any like overhead or anything. Yeah, structs are in C are essentially, this is why C is the fastest, because it's nice and compact. We don't have any prototypes to worry about. We just have this basic struct format right there. Okay, so let's continue on and beyond structures. So I could go on and on about some more complex features. We could do pointers to structures with the arrow operator, but I don't want to get into that because that's painful. And I could sit here for another hour, and we're already 40 minutes over time. But essentially, let's before we end this, I'll just go over some things that we missed. So some things that I didn't cover were switch statements, which for those of you who know Java, I'm pretty sure you all learned switch statements in 201, right? It's a statement that essentially lets you, it's a lot like an if-else chain, except it looks nicer because you're only switching off of one value. The thing with switch statements is switch statements can actually be made to be much faster because they can implement a lookup table, which means instead of going through every condition for an if-else, you can jump to exactly what you need in a one time, right? So that's a nice benefit of the switch statement. In Java, I don't even think they implement it like that. Actually, you know what? It's not Java that doesn't implement it like that. I think that might be JavaScript. Anyway, finally, we have storage specifiers, which auto, register. I'm not going to go over any of those. Static. Static is very useful, but I might go over that tomorrow in the x86 presentation. Enums are basically you're able to assign names to values, kind of like how they did true false, except with define, except not. It's you can store colored names as integers and stuff. Enumerate, essentially, that's what that means. And finally, unions. Oh god, where do I even start with unions? Unions are quite a they're a beast, essentially. It lets you store multiple different variables as in one memory location and then interpret them as different data types, which we are not going to go into because that is going to be very painful. Does anyone have any questions on these before I move on to the demo portion of this? Because I can go over any of these if you want to sit here for another half hour. If not, okay, I will move on. Demos. So I was going to say, yes, let's install a C compiler, except I seem to have gone far over time, and I do not think we're going to have time to install a C compiler. my advice to you is, if you want to install a C compiler, first install the, if you're on Windows. So I don't know who's on Windows and who's on Mac. I unfortunately am not very good at providing advice to people on Mac since I am on Windows. But I do know that the main way that you're going to want to go about on Mac, I'm pretty sure there's just literally a GCC package you can install. Otherwise, you might want to use a virtual machine to install the GCC compiler. Mac is easy for C. Yeah, that's what I imagine. On Windows, it's actually also very easy. You can just do stuff like, so I already have GCC installed with MSys2, but I am not going to use GCC with MSys2 because that is not very easy to set up. Setting up MSys2 takes like an hour, and it's not a very pleasant experience for anyone. Instead, what I would recommend is, for those of you who don't know, Windows has an entire distribution of Ubuntu under the hood now that you can tap into using WSL, which is the Windows subsystem for Linux. And if you enable it, and I'm not going to go over how you can enable it, but once you do, you just type WSL, and now, behold, I have a Linux distribution running right here, and I can just apt-get install GCC, and I have access to GCC right here, and I'm able to compile on that. So, for those of you who are interested in contributing to the operating system project that I'm working on, and I did promise I was going to show off the neither of these VS Code windows or the operating system. Hang on, let me pull up the operating system. For those of you who are interested in contributing to the operating system, I do recommend installing a C compiler, not so you can compile the operating system, but so you can compile the compiler that compiles the operating system, because you need to build a special cross compiler, which I will be going over much more on Thursday night when we actually go into how we're going to build the operating system. Yeah, I feel the same way, Matt. When I first read that you needed to compile the compiler to compile the operating system, I was like, oh no. Oh no. And the reason for that, there's actually a very good reason for that, is the fact that GCC compilers target certain operating systems. So you have to build your own compiler to target your own operating system, basically. And you need to just build it to target like a generic x86 architecture, not a specific operating system. Anyway, I did want to show off just a bit about structs in the actual code of the thing. So I'm going to go over to, I believe it's gdt.h, where I'm actually declaring the struct. This struct right here is actually what we were viewing right here. So this whole memory construct right here actually perfectly lines up with the values that I am storing in this struct right here. As you can see, we have, and of course that closed it the second I clicked on it, and of course that's not the right window. Goodbye. Okay. So as you can see here, we're declaring this struct here, gdt entry, and we start off with from 0, the limit to 15, then 16 to 31 for the base, and then basically U8, that is a 16-bit integer. So this is actually going to be defined to be a short. So you could actually think of this as short, and then this would be char, and these are all unsigned because we don't actually want negative numbers. We don't care. We just want the bit values because most of this is just flags anyway, and addresses are always positive, right? So going through here, we see, limit 0 to 15, base 0 to 15, base 16 to 23. Don't ask me why the heck the GDT's entries decide that they wanted to split random places. Like this, and this all combine into one 32-bit number, but they decided, instead of putting them next to each other, let's just split them up in random parts of the entry. And I still don't understand why they do that, but that's literally in the x86 standard, as in the processor that you're running right now. When you turn, most likely, I probably, unless you're on a phone, you're probably using x86, which means the processor that you are on right now, millions of times a second, is most likely looking into the GDT and finagling with these terrible entries in the GDT table. Well, that's redundant. T and GDT stands for Global Descriptor Table. Yes, but anyway, it's absolutely mental that they would line these up like this and have base over here. Anyway, so as you can see, then we have base here. Then we have our access byte, which is our flags. Then we have our flags here. And this is this syntax right here. This is a special syntax, which means only use 4 bits of the 8 bits. So essentially, even though we're saying, oh, okay, this is a U8, which is char, 1 byte, we're saying, oh, only use 4 bits, and only use 4 bits. And then this special attribute packed says, all right, and now that we've declared that these are only 4 bits, squish them all together and make it just this one object, essentially. And then I'm basically using this in the operating system. I just want to show off the fact that you're using structs constantly for stuff like this, where you want to store different things and then, just pass them around as one object, right? So that is a practical use of structs in the C programming language. So back to installing a compiler. If you're interested in working on the operating system with me, or you want to contribute, and believe me, we're not going to be, I'm not going to make anyone program in assembly. I just thought it would be cool for everyone to, look over the assembly code tomorrow. And so that's really the purpose of tomorrow's workshop, is we're going to be going over x86's relationship with C. So if you thought it was cool when I was going over, I lost godvault.org, didn't I? It's in this one. If you thought it was cool when I was going over all of the assembly instructions in this window, and you actually want to know what all of this means, and the actual stuff that's running on the computer when you compile your C code, then in that case, come to the workshop tomorrow, because I'm going to be going over what all of these instructions mean, and what we're going to be doing, and how these relate with the operating system, and how they translate to C. And yes, I do have a to-do list. It's not written down, but I definitely have I definitely have a to-do list. And I'll be going over the basics of developing your own operating system on Thursday. But of course, to understand some of those basics, like the first thing that you have to do when you're setting up your operating system is to set up your global descriptor table, which, as you can see, I have this gdt.h, which is C code, and I have this gdt.s, which is raw assembly code. And the reason for that is because you cannot call LGDT from this special assembly instruction that actually loads the global descriptor table, can unfortunately not be called from C, which means I have to write my own little assembly program here to actually load the global descriptor table. Even if I can set up the global descriptor table in C, which I do right here, I'm actually setting up the global descriptor table, I'm not actually able to load that. I have to call into the assembly in gdt.s to call this special method to essentially put this into the processor. And that is that is why essentially you need to basically have a decent grasp on assembly to do a bit of OS development. But as you can see, most of my code is still in C, and I'll be going over that a lot more tomorrow, about the relationship between C and assembly, how you can convert between the two, and what we are going to be how we're going to, program an assembly ourselves, and what all of the assembly instructions, at least the ones we care about, do. Really, assembly is a lot like C in the fact that once you know a few of the instructions, almost all of the instructions are the same thing. If you actually look at it, almost every instruction we use is like move, movel, and it's always going to be, and like, especially if you do addition, it's just the add instruction. So despite the fact that x86 has over 5,000 instructions, you're probably only using 50 of them on a regular basis. This one's like LGDT, which you only call the LGDT assembly instruction once in the entire operating system most of the time. So, yeah, it's definitely a interesting dynamic, though, and I hope I've intrigued all of you enough with the allure of x86 assembly programming to come check out the workshop tomorrow. Probably not, since this workshop has gone on now for 2.5 hours. But if you want to come back for round 2 tomorrow, we'll be going over x86's relationship to C. And now, just to finish things off, what else do I have here on the next slide? I wanted to write simple algorithms in C to help show off to everyone, but we're so far over time that that's not feasible anymore. All right, so in that case, I think I'm going to wrap this up here. No one asked any questions. Well, actually, no, I take that back. People asked a lot of questions. No one's had any spoken questions. But does anyone have any questions before we actually end the workshop? Good to hear that you'll be there tomorrow, Brayden. Always exciting to have people excited in x86 assembly. the best programming language, what they used before they decided to, type things out. Any questions on the C programming language? Anything you want to discuss? Nothing. Okay, that's what I like to hear. That means everyone understood the entire workshop. Right. No, I'm kidding. But if you have any questions about C, I've been working in C for 5 years. We also have a lot of experienced people here who have been learning C for quite a while. So feel free to ask any questions you have after the workshop or just at any time at me. And also the UAlbany CompSci server also has a great C channel that I'm active in as well, if you want to join that. And I would say, yeah, that's the C programming language. Thank you for coming to the workshop. I hope you didn't get scared away by pointers.
Thank you, James.
It's a good workshop, James.
Thank
Yeah,
you.
thank you.
All right. Thank you for coming, everyone. Have a good night. Bye-bye.